So in this video, I want to do another example of a splitting field. And so this time, I want to find the splitting field of x to the 6 plus 1. Okay, and I want to start by talking about the roots of this polynomial, which is going to help us figure out what the splitting field is. And then I also want to talk about ways to factor this polynomial, and that will help us identify the degree of the splitting field. But so first I want to talk about the roots. And I want to notice that a root of this polynomial is going to be any complex number that if you raise it to the 6th power, you get -1. So this is going to be any complex number that if you raise it to the 6th power, you get e to the pi I. And so from that, we can see that the roots are going to be any complex number that has the form e to the pi I over 6. And then we could add a factor of pi I over 3, right? Because if I raise this to the 6th power, this could actually be any multiple of pi I over 3, right? So if I raise this to the 6th power, I'm going to get e to the pi I. And then for this one, I'm doing pi I k, and then I have 6 divided by 3, so that's just going to give me 2. So that's just going to give me a multiple of 2 pi I. And so this just equals e to the pi I, which is -1. Okay, so we can deduce that the roots are going to be the simplest one, which is e to the pi I over 6. But then we can add any multiple of pi I over 3. So the other roots are going to be e to the pi I over 2, e to the 5 pi I over 6. Next one's going to be e to the 7 pi I over 6, e to the 3 pi I over 2 is going to be the next one. And then the last one is e to the 11 pi I over 6. Okay, but what's important about all of these is that they're all just powers of this first one. So that tells me that I only really need to adjoin e to the pi I over 6. And just by adjoining that, this gives me all of the other roots. So this is the splitting field of x to the 6 plus 1. Or it's one way to represent the splitting field. Okay. So now the other thing we wanted to do was we wanted to figure out the degree of this. And to do that, I'm first going to try to factor this polynomial. Because it's easy to look at this splitting field and to look at the e to the pi I over 6 and to say, well, this is a root of x to the 6 plus 1. Right, so if I want the degree of the splitting field, I basically already found it, right? It should just be equal to 6, right? Because it's a root of x to the 6 plus 1. And that works if x to the 6 plus 1 is the minimal polynomial, right? So is this the minimal polynomial of e to the pi I over 6? And the answer is no, but the reason for that is because this factors, right? So this factors as x squared plus 1, x to the 4th minus x squared plus 1. And I get this just by using that this is a sum of two cubes, right? So it's x squared cubed plus 1. Okay. And this polynomial is irreducible. This polynomial is irreducible. But which one is the minimal polynomial of e to the pi I over 6? It's actually this one. Okay. This is the twelfth cyclotomic polynomial. Okay, so this is phi 12 of x. There's a general fact about cyclotomic polynomials that they're irreducible. But in particular, the roots of this polynomial are the primitive 12th roots of unity. So they're complex numbers that if you raise them to the 12th power, you just get 1. And it's easy to see that if I raise e to the pi I over 6 to the 12th power, that just gives me e to the 2 pi I, which is 1. So that tells me that e to the pi I over 6 is a root of this polynomial. And so that tells me that actually this is the minimal polynomial of e to the pi I over 6. So finally, that tells me that the degree of the splitting field over Q is equal to the degree of this minimal polynomial, which is 4. So that tells me the degree of the splitting field, and that is it. Thank you very much for watching.